I'm very happy to have here Professor Kulkarni's another student, Jagmohan Tanti. He's going to give a talk on computations for invariant bilinear forms under an invertible linear transformation. Currently, Jagmohan is working in Babasaheb Bhimrao Ambedkar University, Lucknow. Over to you, Jagmohan.
Thank you, sir. So I should be thankful to the organizers for giving me such an opportunity. And there is a best wishes for Kulkarni sir for this birth week. We can say that a happy birth week. Okay, so this work I did when I was a PhD student at Bhaskaracharya Pratishthan under Professor Katre. Kulkarni sir started coming to Bhaskaracharya Pratishthan in 2007 or 8. So I started interacting with him. And then we considered all types of similarity classes of linear transformations and computed the invariant bilinear forms, their dimension, and also talked about the existence of non-degenerate bilinear forms, invariant bilinear forms. So about the existence of non-degenerate invariant bilinear forms have been considered by Professor Krishnandu earlier with a condition on dimension and characteristic of field. That was a Jacobson-Morozov theorem. So here,
are you changing your slides?
Yeah, no, not yet.
Not yet. Okay.
Okay. 1 minute, sir. Okay. So I think here I haven't shared. So okay. Yeah. Yeah. Is my slide? Yeah.
In my slide,
So these are the outline of the topic. We are considering all types of linear transformation, simulating classes of linear transformation for computing the invariant bilinear form on a given vector space. So, yeah. So here we are considering the field to be of characteristic different from 2, and V a vector space dimension n over F. Then set of bilinear forms forms a vector space over F. And if we take one invertible linear map from V to V, then set of T-invariant bilinear forms the subspace of the space of bilinear forms. So here the question is to find the dimension of this subspace of invariant bilinear forms and investigate about whether there exists any non-degenerate form in this subspace. Yeah. So there are certain historical backgrounds. This problem was previously considered by Professor Krishnandu and Kulkarni sir. They were investigating about the question of existence of T-invariant non-degenerate symmetric, skew symmetric bilinear forms. So they were considering this with a condition given by Jagmohan theorem, which establishes a condition on dimension of the vector space with respect to the characteristic of the field. Yeah, so and several other mathematicians have considered this problem, but we can see that second point survey has taken this with the self-adjoint representations. Yeah, so Frobenius also considered self-adjoint. Stengel also eschews self-adjoint. So here, in this work, we had taken very much generalized field of characteristic different from 2, and without any conditions, we had computed the dimension of invariant bilinear forms, and we talked about the existence of non-degenerate invariant bilinear forms. Yeah, so this is the aim of the topic, that we will be uh, giving some certain formulas to find out the dimension of invariant bilinear forms for different similarity classes of invertible linear transformation. And we will be talking about the existence of non-degenerate forms in every case. So these are certain preliminaries. Here we are talking about when a polynomial is called reciprocal of a reciprocal of a given polynomial. So this is a monic polynomial, degree n, 0 and plus minus 1 should not be the roots of this polynomial. Then this f star x equals to x to the power n, f inverse is called the reciprocal of f. And we say a monic polynomial to be self-reciprocal if f of x is same as f star x. So, an example, we can take this f of x equals to x square plus x plus 1 in qx. This is a self-reciprocal polynomial. Yeah, so there is a one result that if we have a so this is a self-reciprocal polynomial, and here typing mistake is there. This if f of x be monic self-reciprocal polynomial and f of 0 not equals to 0, not equals to f of plus minus 1. If 0 and plus minus 1 are not roots, if alpha is a root of f of x of multiplicity m, then alpha inverse is a root of f star of x of the same multiplicity, that is m. So okay, so this is for general polynomial, not necessarily for self-reciprocal polynomial. So the multiplicity of a root of f of x is same as the multiplicity of alpha inverse as a root of the reciprocal of f. Yeah. So its proof we had obtained here. So it's a elementary proof using So polynomial theories. Yeah. So again, example is there that
Jagmohan,
yes.
Professor Kulkarni has a question.
Yes, sir.
So one should be able to describe all reciprocal polynomials over any field.
All self-reciprocal polynomials. Okay.
Over any field. You can say.
Over any field, yeah. So actually, sir, in the next lemma, we can see some characterization about self-reciprocal polynomial over a field. Yeah, like if f of x be self-reciprocal and degree of f is n, then n should be even. This is one condition. And remark is that the polynomial looking like this ci x to the power I, this I running from 0 to 2n is self-reciprocal polynomial, then C0 should be same as C2n, means constant term should be same as the leading coefficients. Okay, and that should be 1. And ith coefficient should be same as the 2n minus ith coefficient. Yes, sir. So is this giving some answer to sir's question? Yes, sir.
Yes, you go. It answers the question.
Okay, sir. Thank you. So this is the definition when we say that a bilinear form is invariant under an invertible linear map T. Yeah, and respectively infinitesimally invariant. So here, whenever we fixed one ordered basis of V over F, then we can see this T as well as B as matrices, square matrices.
So Jagmohan, there is a question.
Yes, yes.
See, for example, you are saying that let fx belong to fx be self-reciprocal, then n is even. So are there any more conditions? Because, for example, x plus 1 is self-reciprocal, and it's a polynomial of degree 1. So are you interested in saying something about the roots?
Yeah, so actually plus minus 1 and 0 should not be the root of the polynomial.
Okay. Plus minus 1 and 0. That's an additional condition.
Okay, sir.
Okay.
So this whole conditions in the definition can be transformed into the formulas or this.
So in the lemma there is an additional condition.
Yeah.
Please go ahead.
So yeah, we can we have written a script B as the all invariant bilinear forms in terms of matrices. So the theory becomes only matrix theory now. We have to do all computations in terms of matrices. So, okay, so here is one definition of self-reciprocal linear operator when we can, yeah, so whenever the characteristic polynomial of T is self-reciprocal, the operator is called self-reciprocal. So, so again, it is to observe that self-reciprocal operators exist only on even dimensional vector spaces. Yeah, because the characteristic polynomial should be of even degree. So initially we worked on it, assuming that the field is algebraically closed because we were classifying all linear transformations with respect to Jordan canonical form by taking in account of Jordan canonical form. So that assumes that the underlying field is algebraically closed. So later, we generalized this with this result, dimension invariance over field extensions. Yeah, so this for this we had taken the condition that invariant factors of the characteristic polynomial under field extension does not change, and we considered the rational canonical form here for our computations. So dimension of the invariant bilinear forms remain same under field extension. It does not change. So there is one another definition that when we say a linear transformation from V to V to be cyclic. So if there exists one vector V such that the set B TV up to T to the power n minus 1 V forms a basis for V. Yeah, so the first result is about this cyclic self-reciprocal transformation. So if we have a vector space of dimension 2n, yeah, if we have a vector space of dimension 2n and T and in cyclic reciprocal self-reciprocal operator, then the linear form, then the space of T-invariant bilinear forms is of dimension 2n over f. Yeah, am I audible, sir? Acharya, sir?
Yes, yes, you are audible.
And my screen is visible, right?
Yes, yes, your screen is also visible.
Okay, okay, sir. So here also we are talking about the symmetric bilinear forms as well as skew symmetric bilinear forms. So in corollary, we see that under the same hypothesis that T should be invertible cyclic self-reciprocal transformation. Then the subspace of
you have to share the
symmetric
screen again.
bilinear forms is of dimension.
Hello.
Okay, okay, okay. Yes, sir. Yes, sir. Yes, yes.
He's speaking, he's using his mobile.
Yeah, is my screen visible now, sir?
Yes.
Okay. One moment.
The only point is that,
Yeah.
yeah.
Okay. So we were talking about the invertible cyclic self-reciprocal transformations. So here the symmetric part and skew symmetric parts are of dimension n, and also we are talking about the existence of non-degenerate invariant bilinear forms here. So this has been proved that okay, we had proved that there exist symmetric non-degenerate and skew symmetric non-degenerate forms invariant under the linear operator as in the
Jagmohan,
theorem.
hello.
Yes, sir.
Yeah, we can see your screen, but we cannot read anything from your screen.
Oh, okay, okay. Actually, this screen is on my mobile. So, okay.
Are you giving the lecture using your mobile phone?
Yeah, right now I'm using my mobile phone.
Then can you make it in the other way around, rotate it and.
Okay, okay, 1 minute. I'm rotating.
We see your SMS. LIC premium for
Is
policy
it visible,
numbers.
sir?
No, yeah. No.
Is it-
So now you have to turn off
Yes,
your
sir.
laptop.
No, earlier form is better. Yeah, now
Yeah,
it's
this is
better.
better. This is
Now
very
it's
good.
good.
This is very
It's
good.
fine. Okay, okay, sir. Thank you. Okay. So here, okay. So here we have computed the non-degenerate invariant bilinear forms also, and for symmetric as well as skew symmetric. Means we had answered about the existence of non-degenerate T-invariant bilinear forms here. Yeah. So this was about self-reciprocal. So then we are talking about invariance under indecomposable operators. So under indecomposable operators, we are taking T to be unipotent, means eigenvalues should be 1 only. So here certain thing is that, okay, if we take basis E1 up to En for B, and okay, so the Jordan block of T looks like lower triangular matrix having 1 on the diagonal entries. So this T of En equals to En, and for all I lying between 1 and n minus 1, this T of Ei is Ei plus 1. So using this condition and the next formula for invariance, we are establishing that, okay, here also we are decomposing C as identity plus nilpotent part. So we are establishing one condition to obtain this X as invariant bilinear forms in terms of transpositions of nilpotent matrix and X. Yeah. So here we have computed about the dimension of T-invariant bilinear forms. So vector space is of dimension n, and T an indecomposable invertible transformation from V onto V with T or minus T unipotent. So here the invariant bilinear forms under T is same as invariant bilinear forms under minus T. So we can consider T to be unipotent. So then the space of T invariant bilinear forms is of dimension n. If n is even, then there exists a non-degenerate T invariant skew symmetric form. And if n is odd, then there exists a non-degenerate T invariant symmetric form. So in the corollary, we are talking about the dimensions of invariant symmetric and skew symmetric forms. So we are saying that if n is odd, then the space of T invariant symmetric forms is of dimension n plus 1, and in the same condition of n, the dimension of skew symmetric forms is n minus 1 by 2. Yeah, and similar type of result we have obtained if n is even. Okay, so here the dimension is n by 2. Yeah. This character x minus alpha to the power is there with multiplicity n, and alpha is different from plus minus 1. So as this is invertible transformation from V onto V, indecomposable and non-unipotent. So here we have shown that the space of T invariant bilinear forms is 0 in this case. Yeah. So then we are taking T to be indecomposable self-reciprocal transformation on V. Then the space of value of dimension n over f. So these all have been obtained with matrix computations. Yeah. So under this hypothesis of the theorem, so here n is even. So the subspace of T invariant symmetric form is of dimension n by 2, and skew symmetric is also of dimension n by 2. And the subspaces contains non-degenerate form. So here we could see a particular pattern of the invariant bilinear forms in terms of matrices. Yeah. And with respect to that, we are able to talk about, yeah, whether it is non-degenerate or degenerate. Yeah. So here again, we are taking indecomposable, invertible, non-unipotent, non-self-reciprocal transformation on B. Then again, the space of T-invariant bilinear forms is 0. Yeah. Next thing is that, yeah, here we are taking vector space finite dimensional over F, T an invertible linear operator, alpha beta from F, and this alpha into beta is not equals to 1. So if x minus alpha to the power r and x minus beta to the power s occur as elementary divisors of the characteristic polynomial of T, then for B, a T invariant bilinear form on B for U belonging to the null space of X means T minus alpha to the power R, and P belonging to null space of T minus beta to the power S, this B of UB equals to 0. Yeah, so this is giving us, yeah. So which entries should, which blocks will be 0? This is giving us an idea. So if B a finite dimensional vector space, T a invertible linear operator, and alpha beta different from plus minus 1, and alpha into beta equals to 1. In the above lemma, we had taken alpha beta not equals to 1. Here we are taking alpha beta different from plus minus 1, but alpha into beta equals to 1. If again x minus alpha to the power r and x minus beta to the power s, these occur as elementary divisors of the characteristic polynomial, then the dimension of the space of this T restricted to this null space of x minus alpha to the power r, x minus beta to the power s is 2 times minimum of r and s. So okay, so this T invariant bilinear forms is degenerate if s is not equals to r, and we have lots of non-degenerate forms for s equals to r. So this can be seen by its matrix computation. Yeah. So here we are answering the same question with invariant symmetric bilinear forms. So it is coming as minimum of R and S, and also about skew symmetric forms. So both are same, minimum of R and S. So am I audible now, sir?
Yes, yes.
Okay. So all these things have been combined here, means if the elementary divisors are some irreducible polynomials with having no root as plus minus 1, okay, so then the dimension becomes 2 times degree of px and multiplied with minimum of r and s. So the degree of px is getting multiplied. So again, here we are talking about, in the corollary, we are talking about the symmetric and skew symmetric counterparts of this, and the dimension is coming as degree of px times minimum of r and s. Yeah. So now again in decomposable operators again. So we are here taking again B finite dimensional vector space, T an invertible linear operator, and R plus S equals to N we are taking, okay. And alpha is different from plus minus 1 if roots are same here, x minus alpha to the power r and x minus alpha to the power s. These two occur as elementary divisors of the characteristic polynomial. Then dimension of the space of T restricted to this subspace invariant bilinear forms is n plus 2 times minimum of R and S. Is this visible, sir?
Yeah.
N plus, yeah. Okay. And again, in the same situation, we are talking about the symmetric and skew symmetric parts, about their dimension. Like symmetric, the subspace of invariant symmetric bilinear forms is of dimension n plus 1 by 2 plus minimum of R and S. And for skew symmetric, it is n minus 1 by 2 plus minimum of R and S. Yeah. So again, with the same hypothesis, if, okay, so here it is an even, then if R is odd, the subspace of T invariant symmetric forms and T invariant skew symmetric forms are of dimension n by 2 plus 1 plus minimum of R and S, and n by 2 minus 1 plus minimum of R and S respectively. So all these things have been obtained with respect to matrix computations. Yeah, if R is even, they are of dimension n by 2 plus minimum of R and S, and n by 2 plus minimum of R and S respectively. So both are same. So again, continuing this under decomposable operators. So here we are taking, so alpha and beta are different from plus minus 1. Alpha into beta is 1. The minimal and characteristic polynomials of T are like this. X minus minimal polynomial is x minus alpha into x minus beta, and characteristic polynomial is this. Then the dimension of the space of T invariant bilinear forms is 2 times RS. Yeah. So here the subspace of T invariant symmetric bilinear forms is coming as R into S. That is half of the dimension of T invariant bilinear forms. So same thing is true for skew symmetric invariant bilinear forms, a subspace of, yeah. If R is equals to S, then there are non-degenerate T invariant bilinear forms, symmetric as well as skew symmetric for this T. Here, okay. So again, here we are considering the minimal and characteristic polynomial of T with polynomials like f of x into f star x. So f of x, f star is x is the reciprocal of f of x, and characteristic polynomial is f of x to the power r, f star x to the power s. So plugging together the polynomial factors and their reciprocals. This was the idea. So okay, and f of x is separable with having plus minus 1 as no root. And this plus minus 1 is not a root of f. And u, a root of f of x, f of u inverse is not 0. U inverse should not be a root of f. Yeah, u inverse is going to be a root of f star x. Then the dimension of space of T invariant bilinear forms is 2 times degree of f of x times rs. So okay, earlier we had done same type of things for P of x, an irreducible factor. Yeah, so same thing here. Subspace of T invariant symmetric bilinear forms is of dimension degree of f of x times rs, and subspace of T invariant skew symmetric bilinear forms is of dimension degree of f of x times r into s. So again here, if r equals to s, then there are non-degenerate T-invariant bilinear forms, symmetric as well as skew symmetric. But infinitesimal version, we are talking about all those results, whatever we have obtained for invariant version, those are true here in infinitesimal version. So here, in place of self-reciprocal polynomials or reciprocal polynomials, we are talking about additive dual of a polynomial. And using this, we are establishing all the results, similar results. So as those results are similar, so here we are not, we have taken it, but it is on in the paper. So something we have written about the additive self-dual polynomials, and in the same fashion we can compute the dimension and talk about the existence of non-degenerate forms in infinitesimal version. So yeah, there are some differences. Thanks. So after, yeah, yes, yeah, if there be some comments or questions.
Yeah. So I have a question.
Yes, yes.
I have seen some of your papers on archive, where I
Okay.
suppose you are trying to generalize it for
Yeah.
for groups or for subgroup of
Yeah.
modular group, something like that, no?
Yes. Actually, at the time when we working, has a hint that this work can be generalized for finite groups of. So I actually gave this problem to one of my certain diet and groups of order 8 and group over 3 where p is an odd prime. So for these 3 types of categories, we could get some answers. Means okay, good answers. So in this way, we are generalizing this result. This was about one linear transformation, and that is the group of linear transformations. So we are again answering the same type of questions for the space of invariant bilinear forms, invariant under a group of linear transformations. Yeah.
Okay.
Yeah.
Any other comments? Okay, so let us thank Jagmohan. Thank you.
Okay, sir. Thank you very much.